Today we're going to talk about heat capacities. The heat capacity is a property of a material, and it lets us find the amount of energy that has flowed into or out of something by measuring its temperature change. Right? Let's take a look at what we've got. So we're going to talk a lot about heat in this video and in the next couple of classes. Heat is a word that actually it's relatively tricky to define. If you ask somebody, do you know what heat is? People would think you were kind of crazy for that. But in fact, if I ask you to write down a coherent definition of heat, it's actually not that simple. First of all, in passing here, our symbol for heat is going to be a lowercase q, right? That lowercase q is actually a tip-off that heat turns out to not be a state function. Right? That means the amount of heat involved with changing the state of something does depend on the path that we take. A definition of heat that is acceptable, that is reasonable, says that it's a transfer of thermal energy into or out of a system. Heat is something that flows from a hotter object to a colder object. Right? Some books actually refer to that as the zeroth law of thermodynamics, that heat will flow spontaneously from a hotter thing to a cooler thing. Heat and temperature are closely related, but they're not actually the same. Okay, temperature is a measurement of how much thermal energy something has, and the heat, Q, is associated with a change in thermal energy, right? So heat is about a process that gets us from one state to another. Temperature, which is an uppercase T, meaning it is a state function, that one is a property of the state that our object or system happens to be in, okay? The idea that these words matter and that they're kind of subtly defined, that's a sort of common feature in thermodynamics. There are a lot of words, including a lot of words that get used in ordinary conversation, like heat and work and energy. But in thermodynamics, it's actually really important that you're using terms correctly and that you do things like make sure that you have a consistent definition of what is the system, the thing you're talking about. All right, so I said we're going to talk about heat capacity, so let's get to that. The heat capacity is a relationship that connects up Q, the amount of heat, and T, the temperature, or delta T, the change in temperature we'll see in a moment, right? The heat it takes to change the temperature of an object depends on a few things. It depends on what the object is made of, right? And that should sort of make sense. There's all sorts of practical applications when, when someone uses a cast iron skillet to cook something, you do that because it's got a high heat capacity, and that means its temperature can't change quickly. So once you get it really hot, it's going to stay at a steady temperature, right? Pan made of copper, for example, can change its temperature quite easily, and people use those for different applications because if you're making sauces and you want the temperature to be able to change rapidly, then you want a pot that will let you do that. So the composition matters. The size, or how big the thing is, that's going to matter, right? It's going to take more energy to heat up a larger object than a smaller object. That should pretty much make sense. The physical state of material would matter too, right? If I was comparing, say, ice to liquid water to steam, all those things are likely to have different heat capacities, okay? And so knowing that it is H2O that I'm talking about doesn't necessarily tell me the heat capacity. Water is the standard example where that comes up, right? The heat capacity of liquid water and the heat capacity of ice are substantially different. Ice and steam actually turn out to be pretty close to the same, but that's just a coincidence. The last thing that matters is the amount of temperature change. If I want to raise the temperature by more, then it's going to cost me more energy. I'm going to have to put in more energy to heat some water up till it's boiling than I would if I only wanted to heat it up to, I don't know, 50 degrees C or something like that, right? That still takes energy, but it wouldn't take as much as getting it all the way to boil at 100 C. So when we work with heat capacities, there's two versions on this screen of what are essentially the same equation. Okay, and this will bother some of you, but it really shouldn't. There's one up here, which says Q is equal to N C sub P times delta T. There's one down here which says Q is equal to M C delta T, all right? The P on there stands for constant pressure. They're the heat capacity at constant pressure. There's also a heat capacity at constant volume. They are not necessarily the same, and so this is for a process at constant pressure, but The thing I want to talk about more is just what's in these equations. So the C's in either case are heat capacities, just in different units, actually, it will turn out. The N or M, so those are the amount of stuff, right? N is a number of moles, just like in the gas law here. Down here, I have the amount of stuff in mass. Delta T, the last piece, is the change in temperature, right? And so that's going to be in temperature units. That should let us figure out what are the units for these heat capacities then, right? Q is going to be in joules because it's an energy, right? It's the amount of heat. N, if I look at that one, that's in moles. Delta T, let's say for the sake of argument that one's in Kelvin, okay? If I look at what it takes to get things to work out there, then I want joules equals moles times the units for the heat capacity times Kelvin. And that means in here, what I need are joules per mole per Kelvin, okay? And so that is a valid set of units for my heat capacity up there. If I come down to the bottom one, I still want joules for the Q. Now my amount is in mass, right? So it's in grams rather than in moles. And that says now I want joules equal, let's say, I've got grams here. I've got my specific heat units. And then I'm going to just say, for the sake of argument, that I put my temperature in degrees C over here, just to be different. Then here I would have joules per gram per degree C. Okay, so those are the kinds of units we will see when we look at heat capacities. The one up top is formally called the molar heat capacity, and the version in the bottom is often referred to as the specific heat, where it's per gram. In engineering applications, you probably see the mass version of that equation more often. In chemistry applications, we sort of probably use moles more often, but basically it just sort of depends on what kind of information we have, whatever is handier. There's one point I want to make here, and that's that the delta T units don't actually matter whether they're in Kelvin or in Celsius, okay? That'll seem weird at first glance, right? But delta T is going to come out to be the same number, the same size, no matter what. Right. To see that, suppose I took some water and I heated it up from let's say 10 degrees C to 20 degrees C, just for the sake of argument. Okay. If I do that, that'll tell me that delta T is equal to 10 degrees C, right? Because I went from 10 up to 20. I take temperature at the end minus temperature at the beginning. So that's 20 minus 10, and that's 10. Suppose I did the same thing, but I wrote my temperatures in Kelvin. In Kelvin, this would be 283 Kelvin, and I'd heat it up to 293 Kelvin, right? So now my delta T for that is, in fact, 10 Kelvin. All right. Some of you at times will find yourselves tempted to say, well, delta T is 10 degrees C, so therefore it must be 283 Kelvin. Don't do that because that says you're changing the temperature by a whole lot more than you really are, right? And obviously that'll make a difference when you put things in there. So really between degrees C and Kelvin, you can just change those units on the delta T's any which way you want because the degrees are the same size. Delta T is a change in temperature. And so that means our delta T number, the numerical value of that will be the same, whether it's in Celsius or in Kelvin, okay? Again, my main point here is both of these equations tell us it's the amount of stuff times the heat capacity times delta T. The difference between them is really just units, right? If I know, say, the molar heat capacity, if I knew this one, and I wanted to know the specific heat, if I know the molar mass of the substance, I can convert the one to the other, right? It's just using the molar mass because the molar mass is grams per mole. Right? So if I took my heat capacity on top and divided it by the molar mass, then I would get the specific heat. Okay, so there's easy ways to convert between those things. You just have to make sure that you're only working with one version of the equation at a time. What you can't do is I can't put grams in here for this one and then have the heat capacity this way, because then my units don't parse, right? And then I still have grams over moles when I get things multiplied out, and I don't want to have that. All right, going to do an example here. This is one where, gosh, if I was doing in-person class, I actually have a collection of blocks of aluminum that add up to 260 grams that I would be putting in some boiling water to get them hot. And we'd be measuring the temperature change for this thing. But here we'll just calculate it, okay? So I'm going to take that mass of aluminum, 260 grams of aluminum. I'm going to heat them up to 100 degrees C by basically putting them in some boiling water. Then I'm going to take the hot metal and I'm going to drop it into 300 grams of water, initially at 22 degrees C, which is around room temperature. And I'm going to try to find the final temperature for the water and aluminum, okay? Pretend I'm doing the whole thing in like a thermos bottle. So it's insulated from the outside world so that heat is going from the hot metal to the cold water, but no heat is being lost from the container as a whole. The heat capacities, it tells me here, for liquid water is 75.3 in joules per mole per Kelvin. The aluminum is 24.3 in joules per mole per Kelvin. Okay, so those are things I'll be using along the way. So here's my my original information, just copied up there. So the driving force for this is what the guiding equation, let's say, is that the heat that flows into the water has to be the same as the amount of heat that flows out of the aluminum. Okay, and so I'm going to set this up by saying that Q for the water is equal to minus Q for the aluminum. Q, the heat, is actually officially, that's going to be defined. Our signs are going to work. So that's the amount of heat going into something. Okay, stuff going in is positive, stuff coming out is negative. Heat is in fact going into the water, right? And so Q for the water is positive. Heat's coming out of the hot aluminum. So Q for the aluminum is negative. The minus sign there will make sure that I have my equation say positive number equals positive number. Okay. Alternatively, if you put absolute values on things, it'll sort of work itself out. Each one of those Q's, this is going to be, let's call it N for the water, C for the water, delta T for the water is going to be equal to minus N for the aluminum, C for the aluminum, delta T for the aluminum. I'm using moles there just because my heat capacities up here are in moles, right? And so that says I'm going to take my grams and convert them to moles. The 260 grams of aluminum, if we look up the molar mass of aluminum, it's right about 27. It's a tiny bit less than 27. And so I happen to have notes over here that tell me that 260 grams of aluminum is 9.63 moles. 300 grams of water at roughly 18 grams per mole says that one is 16.67 moles, okay? And that's just a grams to moles conversion. It's been a while since you had to do one of those, but hopefully you still remember how, okay? What I'm going to do then is I'm going to say that if I just put in numbers for things here, I suppose, my water numbers, oh, I have them crossed up, so I have to be careful here, but my water numbers say 16.67 moles, 75.3, that's in joules per mole. I'm going to change it to right degrees C. And again, I can do that because it doesn't really matter because they're going to be the same number. I'm going to have, actually, let's not write delta T here. Let's write something like delta T for the water is T at the end minus the initial temperature of the water, which is 22, okay? So I'm doing the problem with my temperatures in C. I could turn them into Kelvin, but that just means I'm going to add in 273s and it's not really going to change how anything comes out. So let's not. Over here, I've got a minus. I've got 9.63 moles. I've got 24.3 joules per mole. I'm going to again write degrees C since I'm writing my delta T's in degrees C. And over here, I've got T final, the temperature I'm trying to find, minus 100, because that was the original temperature of the aluminum, okay? If I get to there, there's good news and there's bad news. The good news is I've got an equation that only has one unknown in it, right? It is T sub F. That's the final temperature. That's what I'm trying to find. The bad news is it's in two places, so I still have to do some algebra to get to solve it, okay? And that does provide some opportunities to mess up. Okay, about this minus sign, if you're still wondering about that, notice that over here, delta T on this side is going to be negative, right? Because TF has got to be smaller than 100 degrees, right? The final temperature has to come out somewhere between 100 and 22 degrees because it can't get hotter than the hot stuff or colder than the cold stuff, right? And so delta T is negative, the minus sign makes sure that that side of the equation is still positive because everything on the left-hand side of the equation, rather, is positive. Let's see, if I do this, this says I get 1255 for those things. My units will work themselves out, right? Because the things in parentheses have degrees C on them. So I'm going to end up in joules equal joules on both sides. And so I'll be able to solve, when I solve, I'm just going to get T in degrees C. So the units are the same on both sides, I guess is what I really mean. That's 1255 times, I'm just going to write TF minus 22 there. On this side, I get minus 234 times TF minus 100. And then when I do that out, I get 1250. Please write 1200. And I hate when this happens. 1255. That's still the same number. I get 1255 T minus 27,610. 610. And on this side, I get minus 234T. 4. I swear I write better than that, even though I write badly. This is plus 23,400. Doesn't like 4s. Huh? And if I take that and solve it for T, I just get the T's on one side, get the numbers on the other side. Since my pen is acting up here, I'm going to say that I get T equal to 34.3. And all my temperature numbers in there are in degrees C. So my final temperature should be in degrees C. Does that make sense? It's between 22 and 100, which is the one thing we know for sure has to happen, right? And so it is a plausible temperature. If I had gotten to do the demonstration for you, we would see that it's around what the temperature actually comes out. Typically, it comes out being a little bit off from that because there's some stuff that gets lost. The system actually is losing some heat. I usually heat up the aluminum by dunking it in boiling water. So when I take it out of there, it still brings some boiling water with it. And so it comes out off in one direction or the other, depending on which time. But it does come out right around there, proving that this whole process does work. Okay. There's one other thing I want to mention here. In this case, our calculation is reasonably simple because sort of intuitively, we didn't have to worry about the possibility that anything was going to change phase, right? My aluminum is not going to melt anywhere along the way here. My water is not going to boil because the aluminum's only at the boiling point when it starts, right? And it's cooling off from there. If I had a case where I was going to have a phase change, where something was going to freeze or melt or boil or condense or what have you, then I have to be careful how I do that, okay? And this is one that people do sometimes get perplexed by. So this is a figure that's in your textbook. It is a sort of basically a heating curve where the x-axis is heat flowing into a mass of H2O. The y-axis is temperature. Starting in the bottom left-hand corner, we start at minus 50 degrees C, where my water is very definitely going to be ice, okay? On the right-hand side, we finish up at 200 degrees C, where my water is very definitely going to be steam, all right? I honestly, right now, I forget what mass or number of moles of water this is calculated for the numbers, but it probably says that in the caption to the figure in the book. So let's start on the bottom left-hand corner. If I start down here, this says I have ice at minus 50 degrees C. Heat starts flowing into it, and what happens? The ice starts to get warmer, okay? So in the line here corresponding to process number 1, that says my amount of heat there is, I don't know, let's say NC, where this is C for the ice, times delta T. Right? Because I'm changing the temperature of ice there. It's still ice. It stays ice until it gets to this point, right? At that point on the corner, I have ice at 0 degrees C, okay? What happens to ice at 0 degrees C if heat is flowing into it? It, in fact, then starts to melt, right? it's definitely true that if I say like, oh, I take some ice and it's at say minus 10 degrees C and I throw it into some warm water, what's going to happen to it? The standard person will say right away it's going to melt. But in actuality, it's not going to melt until it warms up to the melting point, right? So here on this line, this corresponds to taking, that's taking ice at 0 degrees C and converting it to liquid at 0 degrees C. Okay, that's what corresponds to process number 2, where it says melting. The amount of heat that takes is N, say the number of moles, times something which is called the heat of fusion, typically written as, say, delta H with a fuse like that. That is the heat of fusion. Fusion is a fancy chemistry book word for melting, okay? Fusion does not want to come out of my pen, okay. So then I get to this corner. At this corner, now I have liquid water still at 0 degrees C, right? If I stop somewhere in the middle here, then I'd have ice water. I'd have some of both, right? When I get to line number 3, now I'm heating up the liquid water again, right? So this one is, the amount of heat involved there is another N times C for the liquid. I'll put liquid, I guess, because they're all water, right? Times delta T, right? If you look at the slope of those two line segments going from the left-hand corner up to the first, to here, line number 1 versus line number 3, the slopes are obviously different. The slopes are different because the heat capacities are different, right? For the liquid versus the solid, all right? And so now I'm heating up the liquid water. When I get to this corner, now I've got liquid at 100 degrees C, and it now gets to boil if heat keeps flowing into it, right? So while I'm boiling it up here, this one would get an amount of heat that is N times another heat, this time the heat of vaporization. Notice that in the phase change pieces, in my heat of fusion piece over here, and in the one I just wrote there is no delta T. Okay, there can't be a delta T because the temperature is not changing, right? The fact that that's a horizontal line on this graph says the temperature is fixed. Okay, so those heats of fusion and heats of vaporization, those will come in units that are energy per mole, say. Word of warning, they're often listed as kilojoules per mole, and the heat capacities, because of the magnitude of them, are usually in joules per mole. So you often have to make sure you fix up some kilojoule and joule issues there. That's one way to mess up some calculations around here. Notice also the horizontal line for boiling the water is quite long. Water happens to have a very large heat of vaporization. That's because of the hydrogen bonds that exist between water molecules in the liquid phase, right? It's the fact that that line is very long and that the heat of vaporization is very large. That's what makes water a good fluid for use in things like radiators, right? Because it's got this large heat of vaporization. So when it cycles between the liquid and the vapor phase, it's exchanging a lot of energy, right? And that's what you want in your radiator. Lastly, if I get over to here, now I've got steam at 100 degrees, right? Because this line here is changing the liquid into steam. I'll put liquid to vapor. And then on this line, I get yet another NC delta T, where this is now C for the vapor, for the steam in this case, and delta T. Okay, the slope of that line number 5 is also different from the others. It actually turns out to be similar to the slope on line number 1 down there, because again, the heat capacities of steam and of ice turn out to be close to the same. But that's not true for everything. That happens to be true for water. Okay, so if I had a problem where I was, say, putting some ice that was down here into some hot water that started up here, then my ice, for example, probably might have to go around this, this bend and get melted. Okay, in that case, when I set up that heat balance, I'm going to have multiple terms on one side, and we'll probably look at a problem like that in class.